You are watching the Cosmic Case Files, a forensic investigation into the universe's greatest puzzles. Some stories are never finished, they're just filed away. Welcome to Chronicles of the Obscure. In this entry, we investigate. What is Tabby's star, and why does it keep blinking like someone's turning out the lights? Our journey begins in 2009, when NASA launched the Kepler space telescope. Its mission: to stare at a patch of sky and watch for subtle dips in starlight, the telltale signs of transiting exoplanets. Kepler revolutionized our understanding of planetary systems. But in 2011, citizen scientists, volunteers sifting through Kepler's data, found something unprecedented. They discovered KIC 8462852, a star later dubbed Tabby's star after lead researcher Tabetha Boyajian. This star would soon challenge our fundamental understanding of stellar behavior and ignite a global scientific mystery. Initially, KIC 8462852 appeared unremarkable. It's an F-type star, slightly larger and hotter than our Sun, about 1,470 light-years away. Its spectral type suggested a stable, middle-aged star. However, its light curve was anything but ordinary. It was a chaotic, bewildering mess of dips and surges that defied all conventional astronomical explanations. Most stellar phenomena cause predictable, shallow dimming. A transiting exoplanet typically blocks 1% to 2% of its star's light. Even large gas giants cause only about a 1% dip. Eclipsing binary stars produce regular, deep dimming. Stellar flares or sunspots have characteristic patterns. But Tabby's star exhibited something far more extreme and erratic. Its light dimmed by an astonishing 20%, sometimes even up to 22% at irregular intervals. These dimming events could last for days, weeks, or even months, with no discernible pattern or periodicity. It wasn't a planet. It wasn't a binary companion. It wasn't anything astronomers had ever witnessed or could readily explain with known astrophysics. The sheer magnitude and irregularity of these dimming events truly baffled the scientific community. A 20% dip in starlight implies a colossal amount of material blocking a significant portion of its light. To put that into perspective, if something blocked 20% of our Sun's light, Earth would plunge into an ice age. This wasn't a subtle anomaly. It was a cosmic billboard screaming for attention. In 2015, Tabetha Boyajian and her team published their groundbreaking paper, Where's the Flux? The paper meticulously detailed the observed light curve and systematically ruled out every plausible natural explanation they could conceive. It was a scientific confession, a candid admission that they had exhausted all conventional hypotheses and were left with an enigma. Let's delve into some of the natural explanations they considered and why each fell short. First, dust. Interstellar dust clouds can obscure starlight. However, dust typically scatters blue light more effectively than red light, causing stars to appear redder when viewed through a dusty medium. But the dimming of Tabby's star was observed to be achromatic, meaning it dimmed evenly across all wavelengths of light. This observation was a critical blow to the simple dust cloud hypothesis. If it were just dust, the star should have appeared significantly redder. Next, instrument error. Could Kepler be malfunctioning? The team rigorously checked and rechecked the instrument's calibration. The data was clean. Other stars in the same field of view showed no such anomalies, confirming that the dimming was intrinsic to Tabby's star. Then came the most widely accepted, albeit strained, natural hypothesis: a swarm of comets. The idea was that a family of comets, perhaps perturbed from a distant Oort cloud-like reservoir by a passing star, could have fragmented. As this colossal swarm passed between us and Tabby's star, it could theoretically block a significant amount of light. However, the sheer scale required for this explanation was staggering. To block 20% of the star's light, the comet fragments would need to collectively outweigh every single comet in our entire solar system by a factor of 100. While technically possible, the probability of such an event occurring and being observed at precisely this moment was incredibly low. The math was strained. It was at this juncture, with natural explanations faltering, that Jason Wright, an astronomer at Penn State University, offered a truly radical alternative. He presented it not as a definitive conclusion, but as a thought experiment, a consideration for when all conventional avenues have been exhausted. What if, he posited, the phenomenon isn't natural at all? What if it's technology? This led to the re-examination of a concept first proposed by physicist Freeman Dyson in 1960, the Dyson Sphere. Dyson imagined what an advanced civilization would do once their home planet could no longer meet their escalating energy demands. He theorized they would eventually seek to harness the entire energy output of their star. How? By constructing massive collectors. A Dyson sphere isn't a solid, impenetrable shell. Instead, Dyson envisioned a Dyson swarm, or Dyson ring. A vast constellation of independent structures, such as solar panels, mirrors, or habitats, orbiting the star. Thousands of them. Millions. These structures would work in concert, catching every photon, every drop of sunlight, to power their civilization. If an advanced civilization truly needed to maximize its energy capture, this is precisely the kind of megastructure they would build. And crucially, if you built enough of these structures, eventually surrounding a significant portion of the star, the light reaching us would be intermittently blocked. The star would dim, not evenly, because the individual collectors would move, cluster, and shift in their orbits, creating irregular and unpredictable dimming patterns. This description, eerily, matched the perplexing observations of Tabby's star. Wright was meticulously careful in his language. He never explicitly said aliens. His argument was purely scientific. If we see something we can't explain with natural phenomena, we should at least consider the possibility that it's not natural. He emphasized that extraordinary claims require extraordinary evidence, and he was merely suggesting a hypothesis to be tested. However, the media, ever eager for sensational headlines, did not exercise such caution. News outlets around the globe exploded with headlines. The story of Tabby's star transcended scientific journals and became a cultural phenomenon. For Tabetha Boyajian, the sudden media frenzy was both a blessing and a curse. While it brought unprecedented attention and funding to her research, it also meant she spent the better part of the next year patiently explaining the nuanced reality. We don't know what it is, that's the point, we don't know. The scientific process is about asking questions and systematically eliminating possibilities, not jumping to conclusions, especially not one as profound as extraterrestrial intelligence. The quest for answers continued. In 2017, thanks to a highly successful Kickstarter campaign, Boyajian and her team secured funding to point more telescopes at Tabby's star. This time, they were ready, and their patience paid off. They caught the star dimming in real time, allowing them to study the light during an actual dimming event for the very first time. This was a crucial opportunity, as previous observations were retrospective, analyzing past data. What they found during these real-time observations was dusty. The dimming was observed to be stronger in ultraviolet light than in infrared light. This specific spectral signature is precisely what you would expect from fine, microscopic dust particles. This was a significant piece of evidence, strongly suggesting that the obscuring material was indeed dust, rather than a solid, opaque object like a megastructure. The achromatic dimming observed earlier was likely due to the limitations of the Kepler instrument's broad band passes. So, was the case closed? Not quite. While the dust explanation gained significant traction and largely quieted the Dyson Sphere hypothesis, it didn't fully resolve the mystery, because here's the thing about dust. It doesn't just spontaneously appear in such vast quantities, something had to produce it. This led to a new set of questions. What kind of event could generate such an immense amount of fine dust? Could it be comets smashing together as initially hypothesized, but perhaps on an even grander scale? Or a planet breaking apart, torn asunder by gravitational forces or a catastrophic collision? Could we be witnessing the aftermath of a planetary-scale impact? These are all plausible explanations for the source of the dust, but they are not definitive answers. The origin story of this dust remains elusive. Furthermore, the dust itself presents another puzzle. It's incredibly fine, microscopic in scale. Such fine dust particles are highly susceptible to radiation pressure from the star. The intense light and stellar wind from Tabby's star should push these particles away. The fact that we are still observing significant dimming due to dust implies that whatever produced it relatively recently, and perhaps continues to produce it. On cosmic timescales, recently could mean within the last few thousand or tens of thousands of years, suggesting we are witnessing an ongoing or very recent dynamic event. Tabby's star is still blinking, still dimming, still unpredictable. The Dyson Sphere hypothesis, while captivating, has largely receded into the background. Not entirely disproven, but certainly less likely given the dust evidence. However, the fundamental question never truly closed. What exactly is causing this bizarre and persistent behavior? The dust explanation provides a mechanism for the dimming, but not a complete narrative for its origin or longevity. The mystery deepened further in 2024, when a new paper introduced another layer of complexity. Researchers analyzed archival data, some stretching back over a century, and found evidence of a slow, gradual dimming of Tabby's star over that extended period. This long-term dimming was distinct from the rapid, irregular dips observed by Kepler. It suggested that two different phenomena might be at play. Two mysteries for the price of one, indicating an even more complex stellar environment than previously imagined. The legacy of Tabby's star extends beyond its own enigmatic behavior. Its discovery opened our eyes to a new class of celestial objects. There are now dozens of other stars that exhibit similar, inexplicable dimming patterns. Astronomers affectionately refer to them as oddballs or dippers. These stars, like Tabby's star, challenge our existing models of stellar evolution and planetary system dynamics. They represent a whole class of objects we don't yet fully understand. And Tabby's star was just the first, the trailblazer that forced us to confront the limits of our knowledge. Here's what we know for certain, even after years of intense scrutiny. A star, located 1,470 light-years away, is doing something we've never seen before. It's not a simple transiting planet. It's probably not a colossal alien megastructure, though the thought experiment was invaluable. But it's unequivocally not nothing. It's a profound astronomical puzzle, a cosmic cold case that continues to yield new clues and deepen our understanding of the universe's vast and often surprising phenomena. And that's why it sits prominently in the cosmic case files. Not solved, not closed, just filed. A testament to the enduring mysteries that beckon us to look further, question deeper, and continue our relentless pursuit of knowledge. This has been the Cosmic Case Files. The investigation continues. Next time, we take the evidence from this case and apply it to an even deeper question. How can a galaxy exist without the dark matter that holds the universe together? Subscribe and hit the playlist so you don't miss it.